Okay, an object is dropped. Its height is modeled by this equation. We're supposed to find out how fast is it falling 4 seconds after it's dropped. Look, if you're holding the object at t equals 0, the speed is 0, right? It's falling at 0 seconds, 0 feet per second. Once you drop it, it doesn't immediately reach maximum speed. It keeps increasing and increasing. So at time t equals 1, so after 1 second, it's getting faster. After 2 seconds, it's even faster. After 4 seconds, then it's really started to pick up some speed. That's what we're asked for, is the instantaneous speed. How fast is it going at this instant? So to figure that out, we need to calculate the limit as h approaches 0 of f of 4 plus h minus f of 4 divided by h. And if you're not sure where this formula comes from, you want to check out another video, because this is the instantaneous rate of change formula. The instantaneous rate of change point is 4, so a is 4 in that formula. Okay. So to do that, we just need to plug in everything where it's supposed to go. 4 plus h, we're replacing t instead of x in this case. Okay, so I'm plugging in 4 plus h right in here. So this part is 100 minus 4.9 times 4 plus h squared. Okay, so all I've done is I've evaluated this is this, because I plugged it into the formula. And then we're supposed to subtract it by f of 4. That means plug in 4 into this formula and simplify. So 4 squared times 4.9, and then 100 minus 78.4, that's 21.6. So I'll divide by h. Okay, and then once we compute this, then we'll have the thingamajigger. We'll have the instantaneous rate of change. Okay. So I can simplify a bit. I can expand this. So 100 minus 4.9. And you can't just square both things inside that parentheses, right? There's no distributed power of exponents. You got to do 4 plus h times 4 plus h off to the side. And if you multiply those off to the side, you're going to get 16 plus 8h plus h squared. That's all being divided by h. Okay, and then we can distribute that 4.9, so it's just some yucky algebra here. I'm going to use quotes for the limit. So we got 100 minus, if I distribute that 4.9 into everything, 78.4. I'm going to protect this all with parentheses because the whole thing needs to be subtracted. 78.4 plus 4.9 times 8, that's 39.2. Plus 4.9h squared. So I distribute that into the parentheses. And then still the limit. I can subtract everything in the parentheses. So make sure you distribute that negative sign. That error happens a lot in this type of notation, is to forget to distribute the negative sign. Okay, so still the limit as h approaches 0. Now if I subtract all the plain old numbers, this isn't magic, this is how it's supposed to happen. 100 subtracted by 78.4 subtracted by 21.6. Oh, I screwed up. 100 minus 78.4 minus 21.6, that makes 0. So this subtracted by this and this makes 0. So all we're left with up top is negative 39.2h minus 4.9h squared all over h. You can factor out an h from the numerator. That's all divided by h. And so that's where the h's cancel out. Now, let's bring back in that limit notation. Now we've done all the algebra. The limit as h approaches 0. The whole reason we did all that is because we had a divide by 0 problem. We couldn't evaluate that limit. But now that we made the h cancel on top and on bottom, Now we don't have a divide by 0 error. Now you can just plug in 0 in for h. So 4.9 times 0 is 0. So they get negative 39.2 for our final answer. So this thing is falling at 39.2 meters per second.